All right, hi. My name is Jakob. I also work in Berlin on AMPEL. I'm distinct from the other Jakob, who you might know, Jakob Nordin. Right, so what I'd like to show today, Jakob showed on Tuesday examples of AMPEL units, and I'd like to show how those fit together to create multi-messenger analyses that can be expressed fairly compactly in a schema that you can then apply consistently to real-time streams, archived data, and also simulated data. So there are basically two ways to do this. The conventional way you would do this is you would have some driving streams, so either the LSST stream or for us, the ZTF stream right now, that you would then compare to some external catalog as new alerts come in. So the thing driving the progress of the analysis would be the optical alert stream. And this is basically the same as looking in your email in the morning and seeing something interesting and then going looking at a catalog, but having it automated and fixed and specified online has certain advantages in terms of repeatability that shouldn't be underestimated. Right, so I've put together a demo unit that does this. It's basically a dummy thing at T2 multi-mess match. And so this is a stand-in for the class of things that would go and query, say, for LIGO bananas or the error ellipses of ice cube neutrino events, and have a list of those in the recent past that it wants to look for optical counterparts to. So I'm going to demonstrate how that works. So yeah, I'm setting up basically an AMPEL. It has a local database. It has a configuration file that completely specifies the environment that you can then store inversion control and go back to later. Be using, that's our scientific program. It's a unique name that will identify all operations that happen on transients due to this configuration. So right, and then you have the analysis schema, and that's basically a declaration. So not a procedural definition, but a functional definition of what should happen when new data come in. And so the stages there's a filter, which in this case is fairly simple. It's applying some basic quality cuts. This is for ZTF data. So it's things like the real bogus score, a minimum number of detections, and some minimum and maximum duration of detections to cut out either things that are known variables or missubtractions. And then you have a list of things that should happen when data are added. So every time a new data point is added, every time there's new detection, certain actions will be triggered. For example, here, the first thing that happens is that the light curves are updated. So we call these states in AMPEL. So the light curve being tracked for each object gets new points added iteratively, actually, based on each alert. So each time you get an alert, you get a new light curve. And the addition of those new light curves also triggers follow-up calculations. So for this one, the demo we put together is that there is a light curve ranking unit. These are all in the GitHub repository that's linked from the agenda if you want to take a look at them. This is something fairly simple. It takes some null model, so just using SALT2 for convenience, fits that to the light curve, fills an alternate model, and then ranks basically spits out the difference in chi-squareds as a score for how much better the alternate model fits than the 1A model. And the idea here is that you're using this to look for things that are not 1As. And then on all those light curves, in addition, you also rank them against your target list. So this T2 multi-messenger match, the demo version of this just keeps a static list that's hard-coded, but like I said, you would want something that is updating itself based on some secondary data source on the fly, and has some conditions that will look for things.
Jakob, the screen is not moving. Are you trying to move through the notebook?
Is it moving now?
Nope.
No, that's bad. Yeah, not sure what to do. So I'm scrolling back and forth. You should be seeing that. If not,
turn off and on the video, or
yeah, I can stop it. I can stop it and restart. Hooray. Okay, trying to find my window again.
You may want to share your desktop rather than the window.
I can, okay. Can you see it now?
Not yet.
Not yet. Okay. Then I'll just share the entire desktop and see, you'll get to see all the beautiful mess that's here. Okay. So now you should see my entire desktop.
No.
Maybe. Nope. Okay. Well, then I'm not quite sure what to do.
I'll try to share the notebook.
Okay, that would be good.
Then you just tell me how to.
Okay, that I can see.
Yeah.
Okay, now if you scroll down to the alert processor definition part, and we're looking at the T2s now. Okay, yeah, and so then there's the T2 multi-messenger match, which is also a unit that's going to take that light curve and then score it against differences in time, in location, and in energy, with various scalings applied to each of those and give you a combined score to how well this matches the items in your target list. Scroll down, please. Okay, so this has now been set up. And you can see here it's going to be running the simple decent filter, and then on each light curve it's going to be running T2 SN comp and T2 multi-messenger match. And then when it runs in cell 6 here, as Jakob is showing, it's going to then run through all of the alerts in this demo bundle and issue updated documents for each. And so in cell 7, you see after this is run, we have 60 from the sample of 200 alerts. We selected 60 of them based on photometric quality alone. Of those, we had 2,298 data points combined into 70 distinct light curves. You'll see that the number of light curves is distinct from the number of transients because certain objects can be detected multiple times, and those are distinct in this for these analyses. You see the states of these things as they evolve in time. And for each of those light curves, the 70 light curves, there are 2 analyses applied to each. So there are 140 documents in the T2 collection. So now if we run, so the next step is then to actually run those calculations. The alert processor only requests that they be run, but in the live configuration, these 2 things are running asynchronously, and the T2 processor picks up new requests for calculations as they run, and they typically appear within a few seconds of a new transient being accepted. Scroll down, please.
You'll have just 2 minutes.
Yes. Outside of the cell. If you click outside of the cell, you actually, okay, right. Then the thing you would do then is to actually bunch these up into a batch that was updated since the last time you ran. And you can then filter these based not only on the alerts themselves, but also secondary properties from the aggregated light curves. So in this case, we're taking only objects where both the light curve fit was significantly better in the alternate model than SALT2, and that had a score less than 1. So we're a good match to our target. And for each of those, we will get the transient record itself, all the data points, the light curves, and the T2 records. And they can do something with those. In this case, it's only just printing them out. As you can see, when Jakob runs this, so of the 60 transients that actually matched, only one of the 60 alerts that passed, only one of those was actually passed the light curve analysis. And then you can use that to trigger some downstream action. You could push this to Sky Portal or so. You could send yourself a Slack message. You could request automated follow-up for this. These are the sorts of things you could do. There is another way to do this, which I'll try to cover in the last 30 seconds, is that in this, having one driving stream is the simplest way, but the way you probably actually want to do this is to have a truly multi-stream analysis, where you have what's shown here in this here schematically in this text block down here is where you have one listener for, say, the public LSST stream ingesting optical data, another one listening, say, for sub-threshold ice cube events on a hopscotch stream, And basically creating new data points, so neutrino data points for one and optical data points for the other. And then you have a combining unit that is then combining those into hybrid light curves. And that has many different kinds of decisions to make as to what constitutes a true association. And we are actively working on how well this can be generalized. If you can actually come up with a general prescription for matching points from arbitrary instruments and messengers. And if that is a thing you're interested in, we are very happy to discuss this point. And that is all I have.
Thank you, Jacob. Is there any question for Jacob? I don't see any question on the chat. So please, if you have some, please post them on Slack.